6 o'clock. Let's get started. I hope I'm not on mute. Yeah. And let me start recording. So tonight we were supposed to review the lecture 18, addition subtraction circuit. And I had one question on the canvas, which I probably answered already in the canvas. So the question was, how come that A, B bar or A bar B is AX or B is practically by doing, like building up the truth table of that expression and just looking at the uh, XOR function, XOR truth table, they're practically the same. So that's the classical definition of the XOR function, which is A B bar or A bar B. Apart from that, any other question from any of you? Yes. Okay. I like to emphasize couple of points here. Like one is definitely that you probably realize that this addition subtraction operation is nothing to do with the arithmetic. It's practically manipulation of logic values, and it's purely logical. Okay, addition, subtraction, and later we'll see the multiplication and division. They're purely logical, and they are manipulated in such a way they generate the result out of this logic operation as we expect. Okay, and it purely and conceptually to do with the value representation of 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 the numbers. Like it's a binary number. We are representing that, and we are representing binary uh, representation of value with logical true and false, and then we are manipulating the logic throughout this logic circuit and coming up with the result as an binary representation. In that sense, it is logical, but it is still generating the outcome that we want to see from an electronic circuit point of view. Same goes with the subtractor here. One important role that you need to understand is that role of 2's complement format. That's the format, 2's complement formats, and its mathematical implication has this circuit build-up implication as well. Since we can, through that 2's complement operation, we know that, and we can deduce that your addition of subtraction operation is nothing but an addition of a negative value represented. So basically, we reuse the addition circuit, just make that incoming value to its complement form, and that makes us enables us to do subtraction operation through the same logical circuit. The third important concept that you need to be clear of is how the overflow is detected. Overflow detection itself is not, detection circuit is not at all like complicated. It's just one simple XOR gate. Why that XOR gate can successfully detect the overflow condition in this addition operation or subtraction operation. That's the understanding you need to be very clear of. Otherwise, it will be like, oh, okay, there is an XOR and we use it, and it kind of a mechanical learning. Otherwise, it becomes a mechanical learning that with an XOR, you can detect the overflow condition in addition or subtraction operation. The beauty lies in the explanation of why one simple XOR is sufficient to detect overflow for the addition and subtraction operation. Okay, any questions so far? till this point? One definite interesting problem around this adder subtractor circuit would be to count the number of logic gates, especially if we want to convert to, let's say, all NAND type of circuit. That would be one problem that you can actually pick up yourself and try to do it. Just see how far you can go there. But one point is there, like if we, let's say, want to make a pure NAND based subtractor circuit, then we need to come up with a configuration, logical configuration of the XOR logic gate with the NAND only expression. Straightforward from the function, it is a 5 NAND gate, but we can more optimize it using to the 4 NAND gate configuration. During our logic value discussion, did we ever explain like how XOR can be built with 4 NAND gate? Anyone remember? Did I do it?
I don't think you did.
Okay, so let's that's fine. Just I want to make sure we can do that. Let me share my Jamboard with you. Okay. All right, so you probably realize that one of the important component in adder circuit is your XOR gate, because half adder uses XOR gate. Half adder uses XOR gate. So I'm just drawing the XOR gate here. Sorry, half adder gate here. This is your half adder, each, let's say, right? So this is output and this is carry out from the half adder. So what I'm saying that this is one important component definitely, and we know how to make it with a NAND. But here how we are going to make XOR with NAND, that's the question. So XOR operation sometimes is denoted with this plus and a circle like that. This is A XOR B. And by the classical definition, it is AB bar or A bar B, which is one way we can do the 5 NAND deduction like this, right? It is by De Morgan, it is AB bar whole bar, A bar B whole bar, right? By De Morgan. That means I have to have 1, 2 NAND, then 3, 4 NAND, and 5 NAND altogether, right? This is the simplest thing. But let's say we are trying to do a minimal circuit for the XOR gate, then how it plays up. Let's try to deduce it in a little bit roundabout way. So we can, first of all, we'll start with the same step. It is AB bar whole bar, A bar B whole bar by De Morgan, right? Just we did like this here. Then what we'll do, we'll basically expand the terms like this: 0 or AB bar, 0 or A bar B whole bar. Then in place of zeros, what I can write down something like this, right? a bar, which is 0 by identity, ab bar whole bar, and in this case I will write bb bar, a bar b whole bar whole. Now from here, what I can write is, using identity, it is a bar or b bar whole bar. What I'm doing here is basically um, combining these two, right? And very layman's term, taking this other a common of them, so it becomes like wait a minute. So it's become no. This is wrong. Yeah, this one. This is a. This is a. A. Take out common out a, and then rest of the term become a bar or b bar whole bar. And similarly, on the other side, we'll pick up this b as a common, and it becomes b of a bar or b bar uh, b bar whole bar whole bar. And now from here, what we'll do, we will apply De Morgan, will apply De Morgan here for these guys and for these guys. Okay, so by applying De Morgan, we have it is a bar or a bar or b bar whole bar, right, by De Morgan. And similarly for the other term, it becomes like b bar or a bar or b bar whole bar whole bar. Okay. Now from here, I can write again by De Morgan applied on this guy. It becomes like a bar or a b, b bar or a b. Okay, now apply De Morgan again on these guys. So this will become something like a b whole bar and b ab whole bar whole bar whole bar. So now you see I have how many nans? One common nans, AB bar, that is one common, one, and then two. So, okay, one, this is two, three, third, and fourth. So your ultimately logical schematic point of view, it will look like this. So I have a NAND A, B, and then this is AB bar, AB whole bar. Then we NAND with A, NAND with B, and this become A XOR B. So that's a four input or a four NAND implemented XOR gate. Okay. So with that, let's try to count the component of these things. How many NAND gates is used for, let's say, 32 bit, right? Let's say this is my problem. How many NAND gates? Let's say two input NAND gates. They're in 32 bit and some with overflow detection. Sure. With overflow detection. Okay. So how do we proceed? We will simply calculate like 32 bit add sum. That circuit will have 32 full adder and it will have 32 XOR for flipping the B input for the subtraction and one XOR. This is for the overflow, right? And then that means this guy is what? This guy is two half adder. I'm assuming we are talking about 1 bit half adder, 1 bit half adder. And there are what? There is one OR gate, one OR, quantity 1, right? And then this guy, each of them has like one XOR, one AND. This means 4 NAND. This is like 2 NAND. And this is like 3 NAND. Remember the OR is like A or B is A bar, B bar, whole bar. So this is boils down to the 3 NAND. So that means this guy has, let me just change the ink, 4 plus 2, 6 NAND. So 12 NAND here. Okay. So that means this guy will have 32 multiplied by 12 plus 3, 15 NAND. And this guy will have 32 multiplied by 4 NANDs. And this is like 4 NAND. So putting them together, it becomes like 32 multiplied by 15, which is, let's say, which is what? 32 multiplied by 15 is 480. So this is 480. This one is 128. And this is 4. So if we add them together, 480, 128 plus 4, we're talking about 612 two input NAND gate. Two input NAND gate that we need to build up a 32-bit adder subtractor circuit with the overflow detection. Question? No? Okay, so I don't have much thing to do tonight with you guys. If you don't have any questions, uh, please complete your projects this part, this logical implementation of addition subtraction. That is the key part you need to go forward, because next step, multiplication and division, needs your addition circuit. So addition implementation in your project. So please work on that. And there is a separate video also on the specifically on the project on how to, some suggestion on how to build up this logical addition subtraction procedure, how to write that, what is the strategy. We have discussed that. Please review that if you have not already done it. uh, and also start writing the project report in partial, right? Like you can finish the one part, write it down. Otherwise, if you crank it up towards the end, it will be much challenging for you to remember what you did, how did you test, and so on and so forth. So please do that. Regarding testing, please do unit test. Don't wait till the end of the project and everything is done, then you start testing. It will be very, very difficult for you guys to debug through the assembly language and assembly programming environment. So I suggest you write some code, assemble it, and at least run some mock-up testing on those part, and make sure your procedures are doing fine with that. With that respect, you can write your own tester function. Like, you don't need to rely on the testing part that I provide. That is more like a system, overall system level testing. Uh, Try to write your own program which calls your subroutine, calls your procedure, and makes sure your procedure does what it's supposed to do. Okay, so do that lower level unit testing first. Make sure your each lower level procedure does its job correctly. That way, your debugging process and overall life in the assembly programming, this project will be much easier. Otherwise, you know why people got out of the assembly programming, because it is hard to do, hard to debug, hard to remember even your own code. So please do follow methodical step by step. Question.
Will you have office hours any other time this week since Wednesday is a holiday?
No, Wednesday I don't have office hour.
Okay, thank you.
Okay, all right then. If we don't have any question, let's stop tonight. Leave early. Work on the project. Work on the project. Get on top of the theories. Thank you. Good night, all, and see you in next week. Next Wednesday is Veterans Day. Class is off, so we'll all see you on next Monday.
Good night, Professor. Thank you.
Thank you, Professor.
Thank you.